Children, in this video I am going to explain you Kirchhoff's current law KCL, which is also known as junction rule. Here N is the node point in which I1 and I4 are the I1, I3 and I5 are the incoming currents, whereas I2 and I4 are the outgoing current. According to Kirchhoff's current law, at any node point, the algebraic sum of all the current is 0. That is sigma I equals to 0. By sign convention, we take incoming current as positive and outgoing current as negative. Here, I1, I3 and I5 are the incoming currents, so they are written with positive sign. I2 and I4 are the outgoing currents, so they are written with negative sign. So I1 minus I2 plus I3 minus I4 plus I5 equals to 0, or I1 plus I3 plus I5 is equals to I2 plus I4. That is, sum of incoming current is equals to sum of outgoing current. It is the another form of KCL. Here one example which is based on KCL, in which we have to find the value of current I1, I2 and I3 by using KCL. A, B and C are the three node points. At node A, you can see 2.4 is the incoming current and I1, I2, two unknown currents are there. At point B, only one unknown current I2 is there, and at node C again only one unknown current I3 is there. So we can start either from node point C or node point B. If we start from point A, we cannot find the value of I1 and I2 because two unknowns are there. So we start with node C. At node C, when we apply KCL, sigma I equals to 0. At point C, 1.8 is the incoming and 2.6 ampere is the outgoing current. So minus 2.6 plus 1.8 plus I3 equals to 0. We do not give any sign to the unknown current. It comes by its own. So in simplifying, we get I3 equals to 0.8 ampere. It is coming with positive sign. It means at point C, the 0.8 ampere current is the incoming current. Now consider the second node, node B. At node B, 2.6 incoming and 1.2 ampere is the outgoing current. So 2.6 is taken with negative sign. Positive sign, and 1.2, which is the outgoing current, is taken with negative sign. Say in the node C, 2.6 was taken with minus sign. The reason was it was outgoing current for node C. 2.6 ampere is the outgoing current for node C, so it is taken with minus sign. But for node B, 2.6 ampere is the incoming current, so it is taken with plus sign 2.6. So I2 minus 1.2 plus 2.6 equals to 0, or I2 comes minus 1.4. It means 1.4 ampere is the outgoing current at point B. Similarly, for node A, at node A, 2.4 ampere is the incoming current. I2 is 1.4 ampere, which is also incoming. So by KCL, plus 2.4 plus 1.4 plus I1 equals to 0, or I1 equals to minus 3.8 ampere. It means 3.8 ampere is the outgoing current at node A. Second law is Kirchhoff's voltage law, or KVL. It is also known as mesh rule. According to Kirchhoff's voltage law, In any closed network, the algebraic sum of all the EMF and potential drop is equals to 0. That is, sigma E plus sigma IR equals to 0. Sigma E indicates summation of all the EMFs and sigma IR indicates potential drop across the various resistances. Here we follow the sign convention, according to which first convention says that when we traverse when means move, when we traverse from negative to positive terminal of cell, EMF is taken positive, otherwise negative. When we traverse from positive to negative terminal of the cell, the EMF is taken positive, otherwise we take it as negative. The second convention says that when we traverse in the direction of current, potential drop, that is V equals to IR, is taken negative. It means if we move in the direction of current, the potential drop IR is taken negative. And when we traverse in the opposite direction of current, then the potential drop is taken positive. To understand the Kirchhoff's voltage law, consider this circuit diagram. It is a closed loop, closed network, in which you can see E1 and E2 are the EMF of two cells. Small r1, small r2 are the internal resistances of the two cells. Capital R is the resistance of the external load, and whatever is written with black pen, that will be given in the question, and the things which are written with the red pen, this we have to write for our convenience. So we mark the point as A, B, C, D, E, F. We mark the current from cell E1 as I1, from cell E2 as I2, and total current through external resistance as I1 plus I2. We also take the loop. Loop 1 is taken anti-clockwise. We can take it clockwise also. It won't make any difference in the calculation. Similarly, loop 2 is also taken in anti-clockwise direction. We can take it in clockwise direction also. In any direction the loop can be taken. Now we apply the KVL at loop 1. In loop 1, that is, loop 1 is A, B, E, F, A. Means we have to start from point A. We will travel from A to B, B to C, B to E, E to F, F to A. This is the direction of traversing of the observer. So observer is traversing in anti-clockwise direction. So when the observer moves from A to B, no EMF is there, but when he moves from B to E, EMF E2 comes in his path and he is traversing from positive to negative terminal. So E2 is taken as negative, minus E2. And when the person moves from F to A, again EMF E1 comes in his path and he is traversing from negative to positive terminal. So E1 is taken positive. So we have put the value of sigma E. Now we will consider the potential drop. For potential drop, you can see A to B, there is no potential drop because there is no resistance. But when the person moves from B to E, R2 resistance comes in his path. So the drop is I2 R2. It may be positive, it may be negative, but you can see the person is traveling from B to E while the current is flowing from E E to B. So person is traversing in the opposite direction of current. Hence, the potential drop is positive. So we write I to R2. And when he travels from F to A, he is traversing in the direction of current. So potential drop is negative, minus I1 R1. So here minus I1 R1 is written equals to 0, and after rearranging we can write it I2 R2 minus I1 R1 equals to E2 minus E1. It is equation 1. For loop 2 is B, C, D, E, B. B to C, C to D, D to E, E to B. So in this loop only one EMF source is there, and when we traverse from E to F in anti-clockwise direction, E to F, we traverse from negative to positive terminal of the cell, hence E2 is taken positive. When we move from B to C, then C to D, we are traversing in the direction of current, so the drop I1 I2 into R is negative. So minus I1 plus I2 into R is written there. And when we move from D to E, there is no resistance, no potential drop. But when we move from E to B, again resistance R2 is there, and we are traversing in the direction of current, so the drop I2 R2 is negative. So we write minus I2 R2. On simplifying, we get equation as I1R plus I2 inside bracket I2 inside bracket R plus R2 is equals to E2. It is equation 2. So we are having two equations and two unknowns, that is I1 and I2. These two quantities are the unknown quantities because rest of the quantities are given in the question. So with the help of these two equations we can find the value of unknown current, that is I1 and I2.